There we go. That's better. So we had in a previous module, we talked about the fission products, the fission barriers. Do you remember what those barriers for fission products were? Yeah,
Okay.
exactly those.
Yeah, yeah.
And the we want to start with the fuel pellet because the fuel pellet has all the uranium oxide pieces in it, right? All the uranium oxide atoms in it.
Yeah.
And those uranium oxide atoms, when they fission, like I get this molecule, this atom, and it's got everything in the nucleus, and it absorbs another neutron. It splits apart into two. It splits apart into two different fragments, and it becomes this particle over here and this particle over here, plus two to three more neutrons, right? So what we want to do is, and what happens is that then stresses the uranium the ceramic fuel pellet. And
Okay.
so the fuel pellet gets little defects in it, little cracks, the gases spill out, and then the next barrier is the cladding. So we got the pellet, we got the cladding, we've actually got the coolant, the reactor coolant, the water itself. We've got the reactor pressure vessel, which is we call the RPV, reactor pressure vessel.
Okay.
And then we've got the two containments. The dry well or the main containment is what we call the primary containment. I'll just write primary with the like that, and then secondary containment. And what we want to do is we we want to keep track of what's going on in the core, and if anything starts going bad, we want to have some protective actions that protect the plant. So if we start, we want to protect the core long before we have problems with the fuel pellet or problems with the cladding, which then stresses the coolant, which stresses the RPV, which stresses primary containment, which stresses secondary containment. We don't want to put any of those at risk. And so if we start to have a problem, let's say a small leak in primary containment, if we have a small leak in primary containment, we want certain things to be automatic. We want things to happen to protect the core, to put the core into a safe place. And so that's where we get automatic protection concepts. And let's clear this. That's where we have scrams. That's where we have interlocks. That's where we have actuations. And that's where we have isolations. These are the key pieces of our idea of protecting the reactor. A scram is pretty basic. So one of the things I talked about Tuesday was where the name scram came from. Have you ever heard that story?
No.
So a scram, SCRAM, is an acronym. And way back on the first nuclear pile, the first time that anybody had taken a pile of uranium critical, was they had one single control rod, one neutron absorber to shut down the reaction in case it got out of hand, because they didn't know what was going to happen.
Yeah.
They were guessing. They were really smart guys. They were trying to figure it out, but they had this one control rod of a neutron absorber. Neutron absorbers are things that if they absorb a neutron, they don't split into multiple smaller particles. So things like boron, hafnium, cadmium, they have a lot of room to absorb neutrons. And they're like neutron sponges. And so they had this single massive control rod hanging from a rope above this pile. And it was the Chicago nuclear pile, or the Fermi pile in Chicago. And it was under a stadium. and they are the benches of a stadium. And this guy, they were like, well, how are we going to release this control rod into the pile if we need to use it? And so they had a guy standing by with an axe. And his job was to cut the rope that was holding the control rod in case they needed to shut down the reaction. So he was the single control rod axe man. Scram. That's where that came from. But yeah. So all the scram is that's when we have a rapid insertion of our control rods, our neutron absorbing rods into the reactor. Okay. We have a core. This is a reactor pressure vessel, and inside there in the middle is this core, and this is where all the fuel is. And then we have control rods down below it, and these go up into the core to shut down the fission process, to absorb the excess neutrons. And one of the things that's important to understand is, erase this. One of the things that's important to understand is that we can't actually completely shut down a reactor to where there's no fissions happening right away. So if I were to draw power over time, and we're cruising along, and this is 100%, and we're cruising along at 100% power, and all of a sudden we need something happen, we need to scram the reactor. It happens pretty fast, about 3 seconds. It goes all the way down here to about 6 to 7%. 6 to 7% power is where that'll get us. And then it decays away pretty fast, but it doesn't go right to zero. So it starts cooling down, and the reactions. So this, let me go back to this point. This point right here is where we start to have decay heat. So initially you have sensible heat, which is just the heat of the reactor, the heat of the rod. Because of how hot the reactor's operating at, it just has all this crazy amount of heat. We put the control rods in, the heat from the fission. And then we put the control rods in, and that immediate heat stops. But we still have some fissions going on, and that's our decay heat once all the control rods are in. And this decay heat starts to slow down it's subcritical, so there's no more chain reaction. So the number of fissions is starting to get fewer and fewer and fewer. But this can be a long time. So one of the things we talked about in a previous week was we talked about how the core, the reactor, if we take the top off the reactor and we have a core with all the fuel in it, next to it we have a fuel pool. And in this fuel pool is where we store all the not control rods, the fuel rods. And so we move fuel rods out of the core about every 6 years. About every 2 years, we change out about a third of the fuel. Excuse me. And we put it in this big pool of water. And what happens in this pool of water is it cools down, and it takes about 10 years for all this decay heat to go away. So these things stay hot for a long time. And so the scram gets the reactor subcritical and reduces power down to decay heat levels within seconds, about 3 seconds. It's really fast. An automatic scram happen. Now you can manually insert a scram. Are you doing the field trip on Saturday?
Yeah, I should be there.
So you'll get to see how we put a scram in manually.
Oh, okay.
Yeah, we're going to show you that. We're also going to show you some automatic scrams. And what we have is we have a bunch of logic of things that cause scrams. And some of those things that cause scrams are reactor protection system. Let's say power gets too high, or reactor pressure gets too high, or let's say we stop having a place for the steam to go, or the pressure in the dry well. If we have indication of a leak out of the reactor, which means water levels going low and or the primary containment pressures getting high. Those kinds of things cause automatic scrams. And this week we're talking about that logic of how that happens. We're talking about actuations and isolations. So a scram is just one of those protective actions. Does that make sense?
Yeah.
Okay. Isolations. Isolations are if I have my reactor pressure vessel over here, and I got the core inside, and this is in primary containment, and I have things that communicate outside of primary containment. So I have reactor feed water that goes into the reactor. Okay. So feed water goes in, and it has to go in through the dry well. So there's a penetration here, right? And what we do is we put isolation valves before and after these penetrations. So steam has to come out of the reactor. So I put an isolation valve before and after that isolation so that we can isolate a leak. If the steam system breaks right here and all this steam starts escaping, we can close this valve and isolate it so we don't lose our inventory. If we have a reactor feed water rupture, we can close this valve. And there's lots and lots of containment isolations. We have sampling connections, ventilation. We have all these different pipes going in and out of primary and secondary containment, and they all have these isolations. So an isolation is an automatic closure of the valves to isolate primary containment from the environment. So this helps keep any of the bad stuff in the non-people space. We don't want to get into the people space. Some of the isolation signals include some same thing that causes a scram. So sometimes you'll get a scram and an isolation. For example, low reactor water level will cause isolations. High primary containment pressure will cause isolations. So these things, and just like a scram, you can also manually put in these isolations. Just like you can manually put in a scram, you can manually put in an isolation. Another thing we have are actuations. So an actuation is the automatic starting of equipment. So if I have, we have our electrical power system. So let's say I've got, you haven't seen our drawing of our electrical power distribution system yet, right?
I don't think so.
Oh, good. That way I can make this as simple as possible, and you won't know that you won't know how bad this is. All right. Just generically, we have couple of transformers that power our medium voltage buses, and
Okay.
something I don't know how important this not important for this course, but just so you know, we have buses that are SH, which is the 6.9 kV, 6.9 thousand volts, and H means high. SM is medium, and it's the 4.6 kV. And then we have SL, which is low, which is 480 volts. And so those are the voltages we're talking about, SM, SH, SL. So these 5 buses that I drew are all SM buses, 4,160 or 4.16, 4,160 volts. And this is SM1, SM2, and SM3. Now down here, or before we get to that, so these 3 buses are powered by this transformer. So this transformer gives them all power. And they have 2 loads on each one. And one of them's a circ water pump, which is a massive 2-story tall pump. And the other one's a condensate pump. So again, a big pump. But they also provide power to these 2 down here, which is our safety related buses. Now, these buses are important. This is SM7 and SM8. The reason these are important is because that has our safety related equipment, which means the things that we need to do to put to shut the plant down in the event of a loss of power. So if we lost all, if the we had a reactor scram, which means we're no longer making electricity, and we lose our connection with the grid, we still have to be able to operate pumps and provide cooling to the reactor. Because if you think of Fukushima, right? If
Yeah.
you lose the ability to cool, bad things happen. The core melts down, it melts out the bottom of the reactor vessel. We don't want that to happen. And so these two buses are very, very critical to preventing that from happening. And so one of the things we have a backup or we have a secondary source of power, what we call a startup transformer, that also gives power to these three buses. And then we have a backup transformer that gives power just to SM7 and SM8. So if we lose our main transformer, it goes away, and we lose a startup transformer, and we lose the backup transformer. These buses also have diesel generators, what we call EDGs, emergency diesel generators. And these emergency diesel generators, this is a long story to get to the point of what an actuation is.
Yeah.
Emergency diesel generators
Mhm.
automatically start on the event of low reactor water level or high drywall pressure. And so that's an actuation. That's something starting that we want to happen. In other words, it's automatic starting of equipment needed to mitigate an accident. And so our emergency diesel generators are extremely important to our plant. And that's an example of an actuation. You don't have to be able to draw that or reproduce that. All right. Interlocks. So the other thing we have are interlocks. Now, an interlock isn't as similar to an isolation, an actuation, a scram. What an interlock is it's a way of protecting equipment by preventing things from happening that shouldn't happen. For example, if we go back to our SM1, SM2, SM3, down to our SM7, SM8, if I started up the diesel generator on SM7, if I started up DG1, and we still have power from our main transformer, I don't want those two to be tied together. I don't want the diesel generator powering our main transformer while the main generator is powering the main transformer. What happens when two electrical sources try and power this each other? One of them drives the other one, but they're both trying to drive. It'd be like putting two four-wheel drives uh, back to back, putting a chain between them and putting them both in four low, and they try and pull apart, right? One of them's going to win. They don't both win, and more than likely they both lose. That's what's going on with an interlock, is it prevents those 4x4s from hooking up and doing a pull contest. Does that make sense?
Yeah.
Okay. So then we have some concepts. Now you're on which team? What's your team name for your project?
I am with Nuke Squad.
Nuke Squad. And you guys are, do you know what two accidents you're studying?
We're doing Idaho Falls, and then we're doing some other thing, some like Demon Core thing.
Oh, the Demon Core.
Yeah, I don't know much about it, but it sounded interesting, so
Man, that's when you read about that's just crazy. We have a much higher level of respect for radioactive sources for fissionable material now than we did then. A
yeah.
freaking screwdriver. To spoiler alert, guy killed himself by using a screwdriver on this demon core. It's just nuts. But yeah, that'll be fun to research.
Yeah.
So Idaho Falls coincidence. So I'm trying to think of a tie into coincidence and redundancy. Brown's Ferry is the best one for, well, that's for diversity. So let's go back to reactor water level. Okay. I have the reactor
Hmm.
and I have the core and I have a way of detecting water level. Okay. I measure the water level in the reactor. And if it starts getting low, I want something to happen. And that's where the actuation comes in. That's where the scram comes in. So, what if in this setup, the logic, I have some electrical components, I have some relays, I have some contacts. I have 120-volt power going to a contact, going down to a relay. Oh, that's a horribly drawn relay. There we go. And this relay powers this other contact over here and causes an actuation or isolation, something like that, right? What if this relay just goes bad? We'd have a scram. We'd have a scram. We'd have an isolation. We'd have actuations. We'd have things happening that we don't want to happen. So, what we do is we have multiple or redundant um, ways of detecting this signal. So, just trying to figure out how to draw this on here. Instead of just one, I have two. And actually, we have like four. Four is pretty normal for us. And so if this relay goes bad, but this relay here doesn't, if it, wow, that was weird. If that relay says, no, that there's nothing wrong, this is fine, then we don't get a scram. We don't get the actuation. We don't get the isolation. And we have four of these things. So this is how I'll draw it. So that if any one of these components goes bad, we don't get the isolation or actuation. The other thing we have is logic systems, such as 2 out of 2 taken once or 1 out of 2 taken twice. And that means that I have different channels. So let's say this is contact alpha, this is Bravo, that was a bad B, this is Charlie, and this is Delta. And then these are split. These two make up channel alpha, these two make up channel Bravo. And so if I have a 2 of 2 taken once, then that would mean I need both this relay and this relay to actuate. I would need this contact to open or close and this contact to open or close to say, yeah, hey, we really got a signal. And if Bravo and Delta don't do anything, then it doesn't matter. I've at least got 2 of 2 taken once. The way to think about the 2 of 2 taken once and the 1 of 2 taken twice is, are you familiar with logic systems at all, or logic gates and stuff?
Not really.
Okay. The whole idea is if I have a thing one and a thing two and a thing three and a thing four, 2 of 2 taken once is an or. I need those two or those two. And then 1 of 2 taken twice, I need one of these two and one of these two. So one of those two and one of those two. And this doesn't matter so much, except it's really talked about. It's really focused on for several pages in your system description, in your system text here. And so, and it is a quiz question. It's going to be on your midterm. You have to
Okay.
pick one of those two and explain and draw one of the logic systems. You have to draw something better than this. Draw something more like what's in your book. But this is the best way to think about it. One of them's either an or statement or one of them's an and statement. You either need both contacts in one channel. This is what splits channel alpha and channel Bravo, or you need one in each. The other thing we have, piling on, the other thing we have is coincidence. Um, if a, what's it, a good example? Reactor. So go back to the same example we've been talking about. We have the reactor pressure vessel, we have the core, and it's in primary containment. If we have a rupture in one of the pipes and water starts pouring out, we have reactor water level goes low, but also drywall pressure goes up. And so I have two uh, instruments, more than one instrument, um, of different types can tell me something's wrong. So I can set up a logic system that says, hey, if I get a reactor water level and a drywall pressure, then make this happen. Well, what if I have four sensors, four redundant sensors in reactor water level and four redundant sensors in drywall pressure or primary containment pressure? I could set it up so that my logic, I don't have to have two reactor water level or two drywall pressure, containment pressures. I could have one of each. So we can get fancy. The whole idea here is a scram is a big deal. That's a big transient on a reactor. And we don't want random, unnecessary scrams. And we do have equipment that fails. For several years now at Energy Northwest, we've been dealing with what we call ASD, and they have some circuit boards. They've got some capacitors on there that have been failing because they were old and their manufacturing wasn't up to the specs that we needed, and so we have these components fail, and that happens everywhere you go. Ford was dealing with that when they had the circuit shortage, right? The computer chip shortage. Ford was farming out or buying some cheaper computer circuits that were failing. People were having windows roll down automatically in their Ford trucks and stuff. That was just in the last 2 years. So things happen like that, and we don't want to put the plant or the people around the plant at risk for something big like that happening. Okay, so that's the point of all that. Fail safe. So this is one of the I'm going to simplify this and not talk about this a lot. Fail safe's one of the harder ones for people to understand. You will have to talk about that in one of your quizzes or on your midterm. I think it's on your final too. The whole idea with fail safe, if we go back to our power, our buses, and a contact goes down to a relay, and this relay powers this contact, and it needs something to happen, right? Well, this all takes power, right? DC. This all takes power to happen. And so, what if we lose power? Well, we don't want actuations and isolations and scrams to happen just because we lose power. So, a fail safe, you could set up a circuit. Imagine you had a burglar alarm you were building for your house. You would want it to be set up so that if they cut the power to the house, that wouldn't cause your alarm to go off automatically, right? You'd want it to something else to go off. So what we do is we have these contacts closed normally, and these relays energized normally, and this contact closed normally. So what happens is in a fail-safe situation, if we lose our power to this circuit, this contact opens, this relay de-energizes, this contact opens, and it puts the plant in a safe condition. So I guess to restate that better, we don't want a loss of power to prevent us from putting the plant in a safe condition. We want to be able to put the plant in a safe condition even if we don't have power. And so fail safe just means de-energized to trip. Okay? De-energized
Okay.
to trip. So we keep the circuit energized normally, and then if something we lose power, that's the same as causing the signal. And that's where we get into the logic diagrams, which we've kind of already covered here. Um, 1 out of 2 twice, 2 out of 2 once. You got a bunch of, and there's other logic types. You know, even your car has logic types set up in it. Your ABS system uses
Yeah.
logic types to determine whether your brakes are going to, your ABS system is going to actuate or not. And it uses, I don't know exactly what type of logic system, but some type of, hey, let's check on that. There's a type of cruise missile they were testing, saying, "Hey, how can we have a more accurate way of guiding?" This is going to sound like I made this up, or this is some internet lore. This is true. Okay, just look it up when we're done if you want.
Okay.
This is That's how crazy this is. So they were trying to figure out how to get cruise missiles to find a target and track that a moving target. And so this one guy said, "Well, let's train a pigeon." We'll train a pigeon by having it peck at this image of, say, a cruise ship or a cruiser, military cruiser ship or something, and it will peck at it, and it'll look for that and peck at it, and we'll feed the pigeon every time it pecks on that image. And what they found is after a while, you could stop feeding the pigeon, and it would just peck on that ship, and so it would, and then if you release a pigeon, it would find that ship and hone in on that ship. But you wanted it to peck at the image. And so they put this in a missile, this pigeon, in this camera system, and the where the pigeon pecked is where the missile would go. And as long as the pigeon was pecking on the image of the ship, it would go towards the ship. But what if it was a different ship? What if it got distracted? What if it got confused? So the genius idea they had was inside this missile, they set up 3 screens with 3 pigeons and the same image on all of them of the target, the ship, from the camera. And as long as at least 2 of the pigeons picked the same ship, the missile would go that way. So any one of these 3 could get distracted or not peck at the ship or something at any point in time, but it's still, and what they found is 100% of the time the missile would hit the ship because of this 2 out of 3 logic. So
Yeah.
just a crazy example of logic systems. And you can have other types. Your text talks about 1 out of 3 or 4 taken twice. It doesn't matter. Those don't matter. All right, now to the one talking about diversity and the divisional concept. So the Browns Ferry. Have you read about or heard about or talked about the Browns Ferry fire much at all yet?
Not yet.
Okay. So at a nuclear power plant where you have the primary containment and you have all these penetrations, reactor feed water, you got ventilation, you got steam coming out, you got all these penetrations going through this primary containment. And in here has to be a lower pressure than outside so that if any fission products leak out, they don't get in outside of primary containment.
Yeah.
So what they need to do is they always need to check to make sure that this is a lower pressure in here. And so what they did is they would hold a candle next to this penetration. And they just hold this candle with this little flame. And as long as the flame tended towards the penetration, that meant there was a vacuum inside. Well, they caught fire to the insulation and they basically almost burned a plant to the ground, a nuclear power plant to the ground. Well, the crazy thing, and the reason we're talking about this is when we go back to looking at that SM7, SM8, so we got SM1, 2, 3, SM7, SM8, these critical, the safe shutdown things, like we have a CRD pump, we have a Lipkus pump, we have an RHR pump, all these different pumps, and we have some on SM7 and some on SM8. And that's Makes sense, right? You want two of a thing so that if one fails, you can still do the thing. Except that before the Browns Ferry fire, let's say we have a Lipkus pump or a CRD pump here and a CRD pump here. What happens is they routed all the cabling for both those pumps together. They routed all the cabling for both of them together. And the fire happened, and this cabling gets hot and it burns through. And what they had is they had no CRD pumps, they had no Lipkus pumps, they had no RHR pumps, except for sometimes because all the cable, all the wiring and insulation was getting burned. And it would, when it burned, it would take out both systems, right? Because it's all
Yeah.
wired together
Yeah.
in one big wiring bundle. And so they were having equipment start and stop, and it was just going crazy. Well, we have now what we call divisional separation. We're required to, by law, route these cable, all the wiring for these things through different pathways, through different rooms, through different hallways, divisionally separated. We have to keep it completely separate so a fire in one spot doesn't affect the other one. And that's the divisional concept. Safety equipment's grouped into two or more divisions, physically and electrically. So we have to keep things in different rooms. We have to keep the cabling separated. Um, and that's going to be the important stuff. That's the emergency diesel generators, uh, core cooling pumps, cooling water, containment isolations, any emergency filtration equipment, that kind of stuff will all have that divisional separation. Okay. You keeping
Yeah.
up?
Yep.
All right. Topic shift. Now we're going to go back to our fission product barriers, but we're
Okay.
also going to talk about a new thing, and that's our emergency center activations. That's our emergency response. So, of those six barriers, there's three that are really, really important. So, we have fuel cladding. I mean, they're all six important, but there's three that we watch for RPV, our reactor pressure vessel, and our primary containment. We watch these three to determine if there's an accident at the plant. And what we have is we have four different levels of accidents. So we have a unusual event or a UE. This is the lowest level of accident. We don't take any, we don't evacuate anybody. We don't, we tell the the city, state, county, but we don't do anything. We don't even activate our emergency response centers. This is just, hey, this thing happened. It's a minimum consequence. We're not worried about it. And what that could be is a degradation of any one of those three barriers. So if we just lost primary containment, but we still had our fuel cladding intact, we still had our reactor pressure vessel intact, then there's no danger to the public, right? We still have two barriers in place.
Mhm.
So we would call an unusual event and take actions to try and fix it. So the next one, the next level up is an alert. And you'll have to know all four of these levels. And an alert is a breach of either the reactor coolant. I put RPV. I meant reactor coolant. Well, that's fine. RPV. A breach of the RPV, so a break in the RPV, or the fuel cladding. So if one of those two breaks, which is closer to the fissionable products, right, to the fission products, to the after effects of the uranium fissioning, which are really, really radioactive and really dangerous to the public. So if either one of those that are closer to the fission products breaks, Then we declare an alert. Okay. Oops. And then for an alert, what we do is we have a bunch of people were wearing pagers. We got away from pagers recently, so now we're just relying on our cell phones. But if there was an event happened at the plant and an alert went out, a bunch of people off that are on duty would respond, and they'd man up these emergency response centers, and then they would take care. They would address the issue. Um, they assist the operating staff. It's just extra people. Hey, we need extra people to help. And we bring the extra people on site and we help. We don't tell the public to take any iodine. We don't tell the public, we don't evacuate. It's just, hey, we need extra help at the plant. The next one is where things get a little heavier. It's called a site area emergency. A site area emergency is a loss of any two of those three barriers. So I could lose the fuel cladding and the RPV, or primary containment and RPV for primary containment fuel cladding, any two of those three, and we declare a site area emergency. Now, for a site area emergency, we do the same thing we do for an alert. We man up these emergency response centers, but also we evacuate all unnecessary people off site. And this is the one, SAE is the one you'll talk about the most on your quiz, your midterm final. We ask you, hey, which one do they recommend iodine for? Which one do they evacuate all people from the site, unnecessary people from the site? And it's SAE, site area emergency. We in the plant can't tell the public, hey, you need to take iodine. Do you know what iodine does? Do you know why they say take iodine during a reactor?
Uh, it swells up your
Thyroid.
thyroid. Yeah,
Yeah. And what it doesn't just swell it up. What it does is your thyroid is going to absorb all the iodine that's available.
yeah,
And iodine is one of the highly radioactive isotopes that comes out of a reactor accident. And so you don't want it to fill up with the radioactive iodine, but it can only hold so much iodine. So what you do is you take non-radioactive iodine so that it fills up with that, so that when you get the radioactive iodine, it doesn't affect it.
yeah.
That doesn't protect any of your other organs,
Just the thyroid.
just the thyroid. So I died of radiation, but at least my thyroid was good. I don't know. um, but so what we do is we make a recommendation and we tell the city, county, state, say we recommend taking thyroid or taking iodine for your thyroid. And then they'll tell the public, hey, issue this iodine. And I actually don't know where we would get it from here. I know when I was part of the emergency response center in Hawaii that it was at the schools. Uh, in the event there was an accident at the Navy base and a reactor had an issue, all the iodine was stored in the schools, and we would go to the schools. So I don't know. I don't know where it would be issued from here, but somebody would let us know. The other thing we do is we recommend evacuating schools within 10 miles of the plant. And then any recreational areas. So the recreational area that we would worry about is the Horn Rapids area. They've got
Yeah,
a golf course there. They've got the bike track, all kinds of stuff out there. So we would recommend evacuating those areas. But again, those can only be directed by state and local government agencies. We can only make recommendations. And then we got the last one, the GE, general emergency. Now, the general emergency is loss of NE2, which we're already at an SAE for loss of NE2, and loss or potential loss of a third. So, this is gone, and hey, primary containment's starting to crack. We're escalating to a general emergency. And we do the same thing we do for SAE, the site area emergency, except for we also evacuate all members of the public within 2 miles of the plant and 10 miles downwind. Yeah. Um, any questions on those four?
Um, no, I think I got it. I mean, so like for the SAE, it's a loss of just those three barriers.
Two, any two of those three.
Yeah, yeah. Okay.
Yeah. And for these emergency, remember we have six barriers, but these
Yeah.
are the only three barriers we worry about. These are the only three, well, these are the only three we care about for our accident
Okay.
response because those are going to be the three that are really indicative of a problem that can dose the public.
Okay. Yeah, I think I'm good.
Okay. That's all the material. I can't think of anything else unless you have any other questions.
Um, no, I think I'm all set.
Okay. All right. I hope this was helpful.
Yeah, thank you for
Um,
taking the time.
what do you think of this whole writing on the screen thing? Was that easy to see?
Yeah, yeah, that actually worked pretty good.
Okay, good. It's a new thing I'm trying.
Yeah, yeah, it was good.
All right. Well, I'll let you go. Have a good night.
All right, you too.
Bye.
Bye.